Welcome to The Explainer. Today, we are tackling a real classic, a physics problem from the famous Irodov collection. Now, this is one of those problems that, I gotta say, trips up a lot of students. But don't you worry, we're gonna break it down into a simple 2-act story, and by the end, you'll see exactly how to master it.
You know that feeling, right? You're trying to push some heavy piece of furniture across the room. You push, and nothing. You push a little harder, still nothing. Then, all of a sudden, it just breaks free and lurches forward. Well, today, we're going to dig into the physics behind that exact breakaway moment.
All right, so like any good story, we have to set the scene first. And for a physics problem, that means we have to really, truly understand what's being asked. So let's get into Act 1, just decoding the problem itself.
Okay, so here are the key players in our little drama. We've got a block, mass m, just sitting on a flat surface. Now this surface is nice, it's got some grip to it, a friction coefficient we'll call K. And here's the real twist. The force we're applying isn't just one constant push. It starts at 0, and then it steadily grows over time, following the rule F equals A times T. Our job, our big goal, is to figure out just how far this block moves after a certain amount of time has passed.
It is so important to visualize the starting line. Right at the beginning, at time equals 0, our force, A times T, is also 0. So nothing's happening yet. The block is perfectly still, the stage is set, and the curtain is about to go up.
And right here, we hit our first major plot point. This is probably the #1 most common mistake students make on this problem. It's so tempting to assume that the block starts moving the instant we start applying a force. But, you know, friction has a little something to say about that.
I want you to think of static friction as the surface's maximum grip on the block. Before that block can go anywhere, you have to break that grip. And this grip isn't random. It has a very specific maximum strength. You calculate it by taking the friction coefficient, K, and multiplying it by the block's weight, which is mg.
So what we have here is a classic duel, right? In one corner, you've got our applied force, Ft, and it's getting stronger with every passing moment. And in the other corner, you have the stubborn, unchanging opponent, the maximum static friction, Kmg.
So, let's think about that. If our push, our at, isn't strong enough yet to break that maximum grip of Kmg, what's going to be the result of this duel?
That's right. Absolutely nothing. The block doesn't move an inch. The static friction just pushes back with an equal and opposite force. The net force is 0, the acceleration is 0, and so the distance traveled is 0. This is a huge part of the solution. For a whole period of time at the beginning, there is literally no motion at all. Okay, so let's get to the climax of Act 1. This is that moment, that instant when the stalemate is finally broken and everything is about to change. This is the tipping point. Our growing force F has finally gotten just strong enough to perfectly match the maximum static friction. Any tiny bit more force and the block is going to move. We're going to call the exact time that this happens T0 or T0. And if we just rearrange that simple equation, we can solve for the exact time when motion starts. That critical time T0 is Kmg divided by A. This right here marks the end of Act 1. For any time before this moment, the distance traveled is simply 0. Okay, the block is finally on the move. But now that it's sliding, a completely new set of physical rules comes into play. So welcome to Act 2, the dynamics of motion.
Because the block is moving, we know the forces are no longer balanced. There has to be a net force. And according to the absolute star of dynamics, Newton's second law, that net force is what causes the block to accelerate. F net equals ma. This is the key to everything that happens next.
So, what are the forces at play now? Well, our applied force, F, is still there, and it's still growing. But that static friction, that grip, it's gone. It's been replaced by kinetic friction, the friction of sliding. Now for this problem, we'll assume the coefficient K is the same for both, so the opposing friction force is still that same constant value, Kmg. So the net force, the thing that's actually making the block speed up, is the difference between our growing applied force and the constant friction trying to slow it down. It's just at minus Kmg. And you can see, because that first term is changing, the net force itself is not constant. And this, right here, is the heart of Act 2. It's the second big trap of this problem. Since the net force is changing with time, the acceleration must also be changing with time. This is so important. It means you cannot, I repeat, cannot use those simple kinematic equations like d equals v naught t plus half at squared. Those only work if acceleration is constant, which it is not here.
So that becomes our big challenge, right? If our acceleration isn't a simple number, and it's changing every single moment, how in the world are we supposed to figure out the total distance the block travels?
So what do? Well, when our basic formulas aren't enough, we have to bring out the big guns. And in physics, that means it's time for a little bit of calculus. Let's walk through how this gives us the final answer.
It's a really logical two-step process. First, to get from acceleration to velocity, we integrate our acceleration function. Then, once we have that, we integrate our new velocity function to get the distance. But, and this is the most critical part, our start time for both of these integrations is t0, not 0, because that's the moment the motion actually began.
And after you work through those integrals, this is what you get, our final complete answer. And look at it, it tells a whole story. For any time up to and including that breakaway moment, t0, the distance is 0. And for any time after that, the distance is given by this beautiful little equation. See? It's a two-part answer that perfectly matches our two-act story.
So the big takeaway here is much more than just the answer to this one problem. It's a whole strategy. In any physics problem, you have to be a detective. You have to look for those tipping points, the moments where the rules of the game change. Here, it was the moment the block started to move. Identifying these different stages, these different acts in the story, is the absolute key to solving almost any complex mechanics problem you'll ever face.
So now, you've got the tools to solve it. But here's a final thought to chew on. What kind of real-world situation could actually create a force that ramps up so perfectly and steadily, just like F equals AT? I don't know. Maybe a bucket being slowly filled with sand, or a very specific type of engine? It's an interesting thing to think about. Thanks for joining me for this explainer.